Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have
Stormlord by Hewson, released in 1989. Programmed by Nick Jones, and the musician was Jaron Tell, I think. So this game is certainly very colourful. I remember when I was playing this game, when I was probably around about 13, 14 years old, something like that. I was actually really very impressed by the quality of the graphics. Okay, to be honest, it doesn't scroll that quickly, but as a programmer, I knew at the time that this game was using a bitmap mode. Multicolor bitmap mode, to be precise, which uses a very large chunk of the Commodore 64's memory for each bank that it wants to display. So I knew that it was scrolling slowly because it wasn't using any hardware tricks to scroll the screen quicker horizontally than normal. It was just basically using the 8-pixel horizontal scroll and then having to update almost the entire bitmap screen. So no wonder it has to scroll quite slowly, because the Commodore 64 needs enough time to be able to update. So this game horizontally scrolls. You basically have to find the, I don't know what they are, fairies or something like that, before the sun turns into the moon. And you pick up various different items along the way. So here I picked up the umbrella earlier on, and the umbrella protects me from the drips coming down, but doesn't protect me from those balls coming out of whatever they are. There's another fairy here, or whatever they are, I have to collect. Now the graphics on this, the main character uses multicolor and also high-res sprites. Most of the main enemies just use multicolor sprites. This little parallax scrolling starfield effect was quite nice, I seem to remember. It doesn't actually use a bitmap mode for the parallax scrolling starfield. It uses character screen. So anyway, here I am trying to get through the level and not doing a terribly good job of it, to be honest. I was never really very good at playing this game. It doesn't really require very fast reactions. It actually requires quite a lot of forethought and planning to avoid these sometimes quite very annoying traps. There's bees here or something like that. I get hit by bees. Very luckily I managed to escape bees. I have the honey here, you see, and oops, there we go. I pick up the key and drop the honey pot, and then the bees go to want the honey. Yeah, well, there we go. I lost a bunch of lives instead. Such is life. Jump over this skull. Luckily enough, the skull doesn't hurt. And jump over the carnivorous plants and skull here. Try and shoot the things that spawn, and then move over, and then I get hit by one of the things that spawn. Oh no, I don't, not quite yet. Anyway, collect another fairy. I think there's 5 fairies on this level. I don't think I quite manage to complete this level. I'm just giving you a playthrough about as far as I can go. Anyway. That platform, oh yes it does. Well, there we go. It killed me again. Some do, some don't. And to be honest, it's a little bit unfair. But such is life. Or no lives, rather. So anyway, let's have a look at the technical details behind this game. So here we are in ICU Debugger. And I really wanted to go into some details about this title screen. You can probably hear that we can hear what sounds like samples. And if we look at the memory display, we can see that the memory display is actually reading through sequentially quite a lot of memory while playing what sounds like samples. This is a very good indicator that there are samples in memory, because this release sequentially read through memory, unless you have a very, very complicated sample playback routine which has quite a lot of compression. This sample playback routine is actually not that complex. So we can hear the music in the background, and while we're hearing this lovely title screen music in the background, I want to investigate this picture that I've just found in memory. And the VIC is currently displaying the last bank, C000 to FFFF. And there seems to be duplicate data in the previous bank. Let's just check that out. And yeah, there seems to be some duplicate data here. So this looks like the color screen data, and then this looks like the actual screen data, which contains the two other colors when it's in bitmap mode. And if we hop back to the previous bank, there we go, we can see the extra data just before the bitmap data here. So it was decompressed and relocated from this previous bank at 8000 to C000, which is the last bank. Anyway, I'm really interested in the sample playback routine, because this title screen is actually sounding really, really nice. So what I can do is that I can open the Vice monitor and debugger interface, which will help us understand a little bit more about the sample playback routine. So what I'm doing here is that I'm doing a watch on the store for the volume write at D418 in hex, which is the SID volume register. And we can see here that it's reading something into the accumulator, shifting it over 1, 2, 3, 4, 5 times, and then clearing carry, and then adding 35 in hex to the value before storing it to the volume register. We end up with 37 in hex in the accumulator that's being stored into the volume register. And if we have a look at the volume register bits, we can see that the first 4 bits are actually the volume, as you would normally expect. But bit 4 and 5, which is 3 added together, is actually enabling the low and high pass, low and band pass filters. So it's setting the filters, low and band pass filters, but it's also setting the SID volume register, and this allows us to play a sample. If this is done frequently enough, then we get lots of volume clicks at different volumes, and we get sample playback. This is how it works on the Commodore 64. So if we advance, we advanced to the next iteration, and we can see that instead of shifting it over 5 times, it shifts it over once instead, and then adds with carry 35 in hex. So I'm interested to see if anything stores into B32, which was the immediate value for the add with carry, in other words, hex 35. And yes, there is. Look, there's a whole bunch of stuff which stores X and Y, and X is the instruction for shift right, and Y is the 35 value, which seems to be enabling the filters and also adding a bit of extra volume to the sample, which is read from memory. So the samples seem to be packed in memory with low and high nibbles, so the low and high 4 bits, because it's 8 bits in total for each byte in memory, so it's extracting 4 bits from each half of the 8 bits in each byte in memory, and then it's storing those into the volume register. Now I'm really interested because this seems to be some self-modifying code. It seems to be self-modifying the code to the extent that it adds a logical shift right and also updates the immediate add with carry value. Now, if we look here in the code and we've scrolled up a little bit, we can see that it's actually having an option to store EA and 30 for the add. So EA is a no operation in assembly language, and it's also adding the option to include a logical shift right, so with 4A and adding 3.5 in hex. So it seems that we have the option of having shifted or non-shifted samples that are potentially having different values added to their volume to make the smaller samples, if you like, less shifted over and have a larger volume range. So this is a rather interesting way of doing it. I actually would have had two different sample routines in memory instead of knopping out and having a potentially superfluous add with carry done. It seems to be done like this so that the music routine can decide how it wants to play back samples in two different ways, plus potentially altering the sample's base volume, plus also altering the filters which are active during sample playback, which is an intriguing way of doing it, but I would have had optimized routines for all of this instead. For example, instead of doing a whole bunch of LSRs, there is an argument here that you could actually have a slightly cycled, quicker lookup table, for example, potentially. But for all intents and purposes, for this sample playback routine, because it's not doing anything else, it's just displaying a bitmap screen and playing some SID music as well, of course, as well as intermixing it with samples or interleaving it with samples. There isn't a great deal of need for complete optimization for this sample playback routine. So perhaps the pros and cons meant that they just didn't want to completely optimize the whole thing. You can see here that I was adding some breakpoints to see if it was actually hitting the version which would add a no-op during the music player, and then I whizzed through at quite a high speed and, well, playing it back normally at the moment, but I think I went into warp mode. Let's go into, does it go into warp mode? No. Yep. Anyway, so I could not find a point during the music playback where it would hit the breakpoint for knocking out the logical shift right. So I'm guessing it just didn't happen. So anyway, that's the title screen. Let's go to the game. So we can see here that the game code now is decompressing, quite significantly decompressing into main memory. We are at this screen here, which has the developer's credit. Now this screen is interesting. We can see here actually that this screen, when it's displaying, shows this PD systems screen, which is the download software stub module, if you like, which still, some of the code still seems to be in memory. We can see up in the top left hand corner of the screen, in inverted commas, data, we saw that actually at 8000 there was a partially blanked out CBM80 bootstrap memory test here, and then the screen data, and then some what looks like code after it. So if we have a look, we can see here that the CPU history just shows that it's waiting for a particular value, just basically waiting for a key. Now I'm actually quite interested to investigate this PD systems code a little bit, there doesn't seem to be too much extra. I mean, the decompression indicates to me at this particular point that the decompression is potentially a frozen program, and the program was frozen at this point where it's displaying this credit screen which is waiting for text, because I noticed that when it was getting into waiting for space to be pressed or any key to be pressed, if we put a breakpoint in there earlier on and then we run the code again and then we restart the animation. So putting the breakpoint earlier on allows me to trap what's happening, and you can see here when it traps earlier on we get to see something rather interesting. So looking at this point here, if we look at the CPU history, the execution history, we can see that earlier on, by a few instructions, it's doing a PLA, STA1, PLA, and RTI, which is quite commonly seen in frozen programs. What it does is that it pulls the last bit of machine state from the stack and stores it into the CPU's data direction register, and also the bank selection register, which is 0 and 1 in hex here, and then it does an RTI, and the RTI quite handily restores the CPU execution to the correct instruction along with the processor flag. So that's why it does this, is that the RTI instruction allows whatever is on the stack to be used as a launch point or a resumption point, if you like, for the rest of the code. And then you can see that the code kind of like resumes. It stores the last few things into the screen border and background registers, and then continues on executing. So what I'm interested here is that I'm trying to see where the program first executing anywhere between 800 and A000. And we can see here obviously that the entry point has stopped at this particular point in the basic code. So we can see here that the basic sys statement has started as we would normally expect. This is the code, just that program state just after loading, of course. So if we double check the program, we can see here that it's got the same sys 2066. Looks like fairly random data, which indicates that it's quite well compressed. I can use the tools to analyze the file, and it looks relatively well compressed. A file that is very optimally compressed will have, well, it should have ideal distribution between all the different byte values. Okay. You don't want to see peaks. If you see peaks in the byte values, it means that the compression has not completely compressed everything. So anyway, going back to the decompression routine, you can see that it's doing a whole bunch of stuff in very low 0-page memory, which again is very typical of decompressing a frozen program. So maybe there was a hacker cartridge used. You know, hacker cartridges were obviously used by developers as well, because the hacker cartridges allowed developers to compress up their final builds, of course, in a very easy and reusable way, and in a way which they knew that would work very well. And of course the compression really helped because, well, this is a hacked version, of course. The compression might have been added afterwards, but I've often seen frozen program compression also used by commercial releases as well, because compression would help tape loading speed and also help reduce disk space. If it wasn't compression supplied by a freezer cartridge, then it would be compression which was supplied or written by the developer or as a tool used by the developer anyway. So compression is very often used. I use compression in most of my releases, and this is my own compression, of course, because I'm very comfortable with the way it works. I know that it does work, and I know that it's very well tested. Anyway, so this is the start of the main program execution as it tries to return back from its restore point. I'm just having a little look through the memory here, just to see what I can see, because I noticed that there was some code in the first screen, the default screen that you would normally see on the C64, which is a 0400 hex. I saw that there was some extra code data here, so I was just having a look at the start of the code to see if it's anything interesting. It's not terribly interesting, to be honest. So anyway, looking back at this PD systems kind of like download software installed message, I'm really still quite interested in that. So I was just double checking here what 64738 in decimal was in hex, because I kind of like forgot. And then I remembered again, it's meant to be FCE2 in hex, of course. So I noticed here, before trying to go to FCE2, I noticed that actually the ROM, kernel ROM, wasn't banked in. So of course I wanted to bank in the kernel ROM before going to the reset routine. So here we can see that what should have been CVM80 was actually the C in reverse was actually zeroed out, which meant that the reset vector, which is checked for in RAM, doesn't actually pass the test, which is actually part of the normal Commodore 64 boot. So if you have a ROM which replaces that part of the RAM, then it will pick up that jump from the ROM, for example, if you have a ROM at 8000 in hex, as opposed to replacing the kernel. Anyway, so I wanted to restore this. So C is obviously the next letter after B, so I replaced the 0 in memory with the proper value C3. And I wanted to just double check what the code at 83F1 did, and it kind of like went straight to this jam, and it displayed a little green screen. So I thought, this is a bit strange, I thought. So instead, what I'm going to do is that I'm going to set the correct bank before jumping to 83F1. This restores the kernel, and you can see that the second instruction was something like JSR FDA3. It was still not cooperating at this particular point in time, so I decided to do it a different way. Go to address, go to PC, doesn't really work. Anyway, so I decided to scroll down, and then I decided that I'd try and trap it in a different way to see actually what it was doing. Go, see what it does. Just stepping over just to see exactly what's going on. It does seem to be actually trying to do, the normal kernel startup code. whole bunch of stuff, setting up screen and things like that. But I'm thinking at this particular point in time that we could try executing the code by restoring the reset vector which is in memory, and then seeing if it executes as part of the normal Commodore 64 reset routine, soft reset. So we'll just restore the byte here. There we go, C3. And then we will just double check that the kernel is in memory, which it is, so it certainly seems to be. The correct kernel reset code seems to be there. So anyway, we will try and run it. And when we try and run the reset code, bing, we hit the breakpoint. Exit out, and we get a slightly different screen, and we get some slightly more interesting data in the background, but still it is not quite right. And I'm thinking at this point in time that perhaps the remnants of the PD systems bootloader, if you like, was only partially in memory at this particular point in time. I don't think it was completely there. So at this point in time, I decided that I would leave the PD systems code for perhaps future experimentation later on, and I would go back to the game. Because I want to have a look at the game, go through some of the technical details behind the game, instead of spending a lot more time on this remnant of the PD systems bootloader, if you like. So we anticipate that there are going to be two different bitmaps. We can see here actually the bitmap, when it's decompressed, before the game really runs proper, we can see that there is actually a score panel, in the bitmap up in the high bank. And once the game runs, the other bank starts to get bitmap data too. But at the moment, this game is actually quite unusual because this game asks to define key sets in addition to the joystick, but we can see here now that the title screen is displaying bitmap data for the title screen. Now, the text in the background is actually not text in the bitmap, and that's because the bitmap data is in multicolored mode, whereas the text looks suspiciously high resolution, right? So we cannot really mix this, because you can see here that you cannot really mix a high-res bitmap and multicolored resolution bitmap. Not when the text data is mingled in with the rest of the bitmap. There's no horizontal split that we could have, which allows us to do this. And we can verify this by seeing the screen data in the top left-hand corner here. The screen data actually only contains the color data for the screen for bitmap. So if we hunt through the memory at this particular point in time, just looking through the memory to see if there's any patterns found here. And we can see here that the score panel display is actually using a text screen, because we could see some text values in a different part of the screen bank. Now, when it comes back again, we can see that this text is reverse text, so it's actually reversed character screen text. And then the color bar information is actually the background color, which is being set in terms of color bars, so we get some nice colorful text. So, going back to this blank area of the bitmap here, we can see that the high-res text is not part of the bitmap. So where is this high-res text coming from? The high-res text that says you press 1 for the keyboard, press 2 for press 5 to start, and the name of the game and the using process. So if we go back, we can actually see, when we go to this bank, we can see that actually this high-res text is actually sprite data. And there's actually quite a lot of sprite data, because the sprites are, it's the grid of sprites, but basically the sprites are not effective. So this allows the game to display nice high resolution text using sprites, while having really nice colourful multicolored bitmap display for what was part of the game level, if you like. So this is a rather interesting way of doing it. It certainly looks quite pretty, I must admit. The high resolution character-based screen with reverse text also allows nice colourful colour bars behind the text. Now, let's go and have a look at the scrolling. So you'll notice that when the player moves each pixel to the left or to the right, the off-screen, non-displayed bitmap will progressively get updated depending on the horizontal pixel scroll position. This basically allows the Commodore 64 to split, updating the bitmap into smaller chunks of memory for each frame, so that by the time the pixel scroll gets to the correct position, then the off-screen bitmap has all of the data needed to then display correctly for the new next character across. And then the bank is obviously switched. So if we jump up onto an area of the level where we can introduce a pixel scroll. Well, first of all, we notice that actually that when the player character sprite flips between the left and the right, we can see that it progressively flips the sprite data in memory, which was rather interesting. It means that the sprite data was updating the flipped versions of the player character sprite. So as the player character moves left and right, we can see that the bitmap data progressively in horizontal bands updates. And I'm guessing here, but it's probably updating a kilobyte or roughly of data every frame, assuming that the screen scrolls at 1 pixel per frame, which it basically kind of seems to be doing that. One pixel per frame is actually quite a nice slow scrolling speed, so this is what we see. And it looks like the entire scroll is split over 8 frames, as we'd normally expect, because there are 8 pixels, 8 fine scroll pixel positions before 8 pixels turns into an 8x8 character block. So you can see that each of the 2 banks of the bitmap get updated, and of course, with bitmap taking up 8 kilobytes at least of memory, you need to have space for the other part of the bank to hold the sprite data and things like that. So you can see how the sprites get updated when the character animates, moves left and right. We can see how the bitmap data gets updated. Now if we look for the stars, we can see that the stars are actually only updated in one of the banks, the bank at 4000 in hex. We can see actually that the star data was only updating at the start of the bitmap data bank, which really kind of like tells me that it was a character-based screen for updating the stars. So if we go back, we can see every time the screen scrolls, it's updating a huge chunk of memory. This game, when it scrolls, it certainly runs through an awful lot of code, and it runs through updating an awful lot of memory. Huge, great big yellow chunks of updated memory, and green chunks, and then of course the blue I think is indicating that there's opcodes being executed, and there is an awful lot of code being executed as well when it does this scroll. So quite a lot of logic being updated per frame. I wonder how much frame time they actually have left. It's certainly going to be quite chunky in terms of CPU time. Anyway, so there we have it. There's most of the technical details behind this game. If you like these kind of technical deep dives, into these old game memories, then please do consider liking or subscribing to this channel, or dropping me a message in the comments below, or you can send me a message from Twitter or Instagram. Thank you very much, and have a great day wherever you are.